So the question is, this was the function that we got as the solution to our differential equation, and we need to find the interval of validity on it. So you had to use a calculator to do that, partially, because there are two things going on here. One, we know that tangent x is undefined at some values, positive or negative pi over 2, positive or negative 3 pi over 2, and so on. Agreed? Everybody agree with that? Sorry, not like, yeah, there we go. Everybody good with that or no?
Yeah.
Okay, the other thing that's going on though is that x squared plus tangent x plus 25 has to be greater than or equal to 0. So what I did was I went in to Desmos and I just graphed x squared plus tangent x. Put that in parentheses, otherwise it messes up sometimes, plus 25. And I said, well, zoom that out a little here. When is that greater than 0? Well, it's greater than 0, you know, at all of these, all these places, to the right of all these places. But the one that I'm interested in is the one that had, what was our initial condition? That x was 0, right? So the one that includes x equals 0. So that would be right here, starting at negative 1.534 and going up into, I get to this asymptote right here, because there's an asymptote in there, right, of x equals pi over 2. And that's the asymptote that we had found, right, that asymptote, pi over 2. Good or no? So the interval should have been negative 1.534 to pi over 2. Does that answer your question? Does that help? Cool, no problem. Any other questions on any of the separable differential equation stuff? One thing I want to note is that I believe it was on number 2 of the extra ones. I, for some reason, put an interval of negative infinity to infinity, but that is not correct. It's far more complicated than that. And I wouldn't have asked you to find it if I hadn't just accidentally screwed that up as I tried to do it in my head real quick. So I believe for number 2, it came out to be y equals negative natural log of 2 minus e to the sine x. Is that right? From the extra problems?
Yeah.
Yeah. And so I put negative infinity to infinity, but that's not right. Because 2 minus e to the sine x would have to be greater than 0, which would tell us that e to the sine x would have to be less than 2. If we were trying to do this by hand, or that sine x would be less than the natural log of 2. And so then we'd have to take the inverse sine of this. Well, if the inverse sine is less than natural log of 2, natural log of 2 is a positive number. So that means we're going to be somewhere in between the first quadrant and the and then back around to the second quadrant. So somewhere in between, you know, starting in the second quadrant, going to the first quadrant. And so if we take the inverse sine of natural log of 2, x should be less than that, but it should be greater than the value in the second quadrant that has this same reference angle of inverse sine of natural log of 2, which would be the inverse sine of natural log 2 minus 3 pi over 2 to swing all the way back around to be in the second quadrant again. I won't put any on that are that difficult for you to find the interval on. I mean, there might be some that are a little difficult, but not anywhere close to that difficult to get that second value over there. But that's what the interval should be for that one, and I'll repost that with the correct interval in a bit. But if you were to go in and just look for when is 2 minus e to the sine x greater than 0, you can look at that on Desmos. Right, 2 minus e to the sine x. And what are we looking for? When it's greater than 0, right? Oh, man. Oh, that's because that's an equals. That's why. Let's try that again. 2 minus e to the sine x, that's much better. So if we're looking for when that's greater than 0, that's from here to here. That includes our initial condition, which the initial condition was x equals 0, I believe, right? For that one. Is that true?
Yeah.
Yeah. So that should be the 0.766 should be the inverse sine of natural log of 2. So if you put that in there, inverse arc sine of ln2, Desmos will evaluate that for you. And if I subtract 3 pi over 2 from it, I should get that value. So anyway, that's that one. I made a small mistake on that, but any other questions on any of the separable differential equations? Figured I should talk about that one real quick. Yes, everybody feels like they're ready for the quiz tomorrow. Questions from the limits multiple choice?
How do you distinguish between, like, if it's free response, how do you know if it's infinity or does not exist? Like, doesn't infinity technically mean does not exist?
Yep, you could write either one in the free response and either one would be acceptable. In the free response. In the multiple choice, they'll either put one or the other.
Could you go over 37, 38, and 39, please?
Sure, what's 37?
Limit of x as it approaches 0 of the square root of 3 plus arctangent of 1 over x.
Okay, the x approaches 0. All right, so this one's a little bit weird to think about, because if you plug in 0 here, right, we think about 1 over 0 is infinity, right, normally? True.
Yeah.
Yeah, 1 over something very close to 0 is like approaching infinity. So this is like the inverse tangent of infinity, which we know is pi over 2. But because this is just an x down here, sometimes when I approach 0, for example, if I approach 0 from the right, then 1 over x approaches positive infinity. But if I approach 0 from the left, 1 over x approaches negative infinity. Do you agree with that? So one case, the inverse tangent of 1 over x equals pi over 2. But in the other case, the inverse tangent of 1 over x as we approach negative infinity equals negative pi over 2. So from the right-hand side, this thing is approaching the square root of 3 plus pi over 2. And from the left-hand side, it's approaching the square root of 3 minus pi over 2. And so since the limits on the left and on the right are not equivalent to each other, we would have to say that this limit doesn't exist. And if we were to graph this function, square root of 3 plus arctangent 1 over x, we would see that from the left and from the right, we get two different values, right? And clearly it doesn't exist. Good or no? That makes sense for
That
that
makes
one?
sense.
Cool. Yeah, so that one's a little bit tricky. What was, let's see, I got
Oh.
the 30,
Could you
38
do-
is like a longer one. Let's do 39 real quick at the same time, because 39 looks to be a fairly similar one. And then we can go back to 38. What were you gonna say?
Oh yeah, just 39. Yeah, thank you.
Are you good with 38 now?
I looked it over. Yeah.
So for 39, it's the limit as x approaches 0 of 1 over, what is it, 2 plus 10 to the 1 over x. And so same kind of concept here. As x approaches 0 from the right, this becomes 10 to the 1 over positive infinity. Or sorry, 1 over positive very small number, which becomes positive infinity, right? And so this becomes 1 over 2 plus 10 to the infinity, which equals, 10 to the infinity is huge. 2 plus a huge number is still a huge number, and 1 over a huge number is 0. But as x approaches 0 from the left, this becomes 1 over 2 plus, well, it's still an infinity here, right? This is still a very small negative, but now it's 1 over a very small negative, which makes that 10 to the negative infinity instead of positive infinity. And 10 to the negative infinity is like 1 over 10 to the infinity. And 1 over 10 to the infinity itself is 0, which gives you a half. So from one side it's 0, and from the other side it's a half. And therefore that one is also non-existent. And if we look at the graph, 1 over, what did we just say, 2 plus 10 to the 1 over x, right? We can see that from the left hand and the right hand sides, we have two very different functions, or different limits. Good or no?
Yeah. Thanks.
Yeah, no problem. All right, give me 1 second, I'll be right back. Okay, sorry about that. Dog is whining to go out. Otherwise, I'm just gonna have to sit and listen to her whine for the next 45 minutes. Okay, somebody was also asking about 28 and 29. Yeah, lots of people actually have now asked me about 28 and 29. So 28 and 29 involve this thing called the greatest integer function, which you should have learned about at some point. Sometimes it's just denoted like this. Sometimes it's denoted with double brackets, but usually they just say it's the greatest integer function. Well, the greatest integer function, you guys have talked about that, I hope, in like previous classes. It's just a step function. It just looks like this. So what the greatest integer function is it says that for whatever x value you plug into it, pick the largest integer that is less than or equal to the number you plugged in. So the greatest integer function for 1 would be 1, because the largest integer that is less than or equal to 1 is 1. Right? If I plugged in, a half, the largest integer that is greater than or equal to a half, is less than or equal to a half, is 0. Right? Half's not an integer, so I look below that. First integer below a half is 0. If I put in 0.99999, well, the greatest integer that is less than that is 0. But as soon as I put in 1, I get to 1. If I put in 1.7, it should still be 1. So all along from 0 to 1, it's 0 until I hit 1 and it jumps to 1. And so I don't know exactly what 28 and 29 were asking, but let's just say we were talking about one of the endpoints. So let's say we were looking for what did 28 ask? Was it an endpoint or was it in the middle of that one? It was in the middle, right? It was a half. So the limit as x approaches a half, well, it's just 0, because from the left, I'm going to 0, and from the right, I'm going to 0. But for 29, it says the limit as x approaches -2. Well, I guess I need another one of these out here. But as I approach -2, from the left, my value is -3. But as I approach it from the right, my value is -2. So it's non-existent. So from the left, it's -3. From the right, it's -2. So the two-sided limit wouldn't exist for 29. But for 28, it's 1/2, because the value of 1/2 from the left and the right, we're still approaching. Or sorry, it's still 0, because the value that we're approaching from the left and from the right is still 0, because that 1/2 is between the two. Does that make sense to everyone? Like 3 or 4 of you asked me about that one in the chat. So is that good or no? Any other questions?
Can you do 19 on the more limits one? It's limit x approaches infinity sine 1/x.
Yeah. So the limit as x approaches infinity of sine of 1/x. Is that?
Yes. Yeah.
So as x goes towards infinity, 1/infinity is what?
0.
0. So we should just be saying this is the limit as x approaches infinity. Should be the limit. If 1/infinity is 0, this is just the limit as x approaches infinity of the sine of 0, which is just 0.
Okay, got it. Thanks.
Mm-hmm. And if we look, we can look at the graph of sine of 1/x. We might have looked at this graph at some point, but you can see it's, we go towards infinity, it's approaching horizontal asymptote there.
Wait, related to Kayla's question, could we do the limit as x approaches infinity of x times sine of 1/x?
Sure. X approaches infinity of x times sine of 1/x.
Yep.
So this one has a little bit of a problem. This one actually is indeterminate, but of a form that I'm still not sure why they put this question in the A/B multiple choice. But the form here is infinity times 0. And infinity times 0 is a little bit of an issue, because infinity times anything is supposed to be infinity, but 0 times anything is supposed to be 0. So we've got this issue here, right, between infinity times 0. I thought I did this problem yesterday. Didn't I do this problem yesterday? Maybe I'm wrong. Anyway, so what you do here is you do a substitution in like u = 1/x. So if u is 1 over x, x is 1 over u. And if x goes to infinity, u goes to 0. So we'd rewrite this as the limit as u approaches 0 of the sine of u times 1 over u. And then this is now 0 over 0, but we know that that value is 1 because we proved it. Or we could use L'Hopital's rule, make it cosine u over 1 and evaluate it that way. Does that make sense?
Yeah, thanks.
Mm-hmm. Other questions from any of the limit stuff? $38, okay. I was just looking at 38 a second ago, right? So it's got a whole bunch of stuff written there. So we got, suppose that we've got the limit. What is it? The limit as x approaches -3 from the left of f of x equals -1. And then we're told that as x approaches -3 from the right of f of x, it's also -1. And it says f of -3 is not defined, so it doesn't exist. And we want to know which of the following statements must be true. So first one, statement number 1, is the limit as x approaches -3 of f of x has to equal -1. Okay? So that has to be true, right? Because our statement of the two-sided limits is the limit as x approaches -3 equals some number, in this case -1, if and only if both the limit from the left and the limit from the right both equal the same value. So that's true. So 1 is definitely a yes. That's just based on the definition of a limit in comparison to its two-sided limits. Number 2 says that f is continuous everywhere except x equals -3. And so this one, that could be true, but there's nothing stating that there aren't any other potential discontinuities for f. It doesn't say f is a continuous function except maybe at -3, right? So this is not certain. It could be true. Oh boy, I really butchered that. There we go. This is not certain. We don't know for sure if that's true. It could be true, but we're not guaranteed from the information given to us. And then number 3 says f has a removable discontinuity at x equals -3. Well, we know the function doesn't exist there, so it's got some kind of discontinuity. It certainly can't be a jump discontinuity because we're approaching -1 from both sides. And it certainly can't be an infinite discontinuity because we're not approaching infinity from both sides. So the only option left is that it's definitely got a discontinuity. It's not jump and it's not infinite. It must be removable. So this is a yes also. So numbers 1 and 3 are true, which means that I guess it must have been answer choice D. Hopefully. That help? Any other questions from any of the limit stuff? All right, sounds like we're ready to move on to finishing up the area things. Does that sound about right to everybody?
Yeah.
All right. We can always go back over some more later on if people have some that come up later on that like you guys to all be trying to get through them as we're moving through stuff. So maybe by Monday or Tuesday, I'd like to start talking about some of the ones from the derivatives multiple choice bracket. So over this weekend, try to get some of that taken care of.
Is there a date for the new derivatives and limits practice you posted that we should have them like completed, like so we can schedule for that, or is it just?
And the new limits one?
Yeah,
like the ones with the one that isn't multiple choice.
Yeah.
Have that done by Monday, and we'll talk about, I guess I did one or two of them off of there I think today, but we could talk about any more of the limits ones on Monday, and then let's say by Tuesday we'll talk about the multiple choice derivatives.
Okay, thank you.
The multiple choice derivatives was pretty long, right? It wasn't like 100 questions or something, wasn't it?
Yeah, it was like 103, I think.
Okay, so maybe let's talk about the first 50 of those on Tuesday, and then maybe by like Wednesday or Thursday we can talk about the other 50.
Thank you.
All right. Here is a good problem for us to take a look at. Looks like we got square root of x. We got x minus 2, and we're talking about the region right here in the first quadrant, right?
Did we already do this?
Oh, yeah, we did. Yeah, we did. Didn't we do it like 3 times?
Yeah.
Yeah. I thought we did. Fourth time's the charm. So let's just do this one more time here, huh? I think that'll be good. So last time we did this where we split it here, right? And we did root x from 0 to 2, and then root x minus 2 from 2 to 4. Y'all remember doing that?
Yes.
Okay. And we also did it where we did root x minus 2 from 0 to 4. We found this whole bigger region and then just knocked off this little triangular piece. True?
Yeah.
And we also did root x from 0 to 4 and then knocked off this other triangular piece. So we did this whole thing, but knocked off this little triangle.
Yep.
Does that all sound familiar? Yeah, we did all that yesterday. Good.
Mm-hmm.
Okay, and the reason we had to like find these ways to manipulate this problem was because one function was always the top, but one function was not always the bottom, right? We had 2 different things representing the bottom of this function. So like there were some x values, like this one, root x was the top and the x-axis was the bottom, but this x value, root x was the top and x minus 2 was the bottom. And it was an issue. True? That's the whole reason why we had to do multiple different, well, we had to either do multiple integrals or find this like, weird way to do it with the geometry. So what we're going to do is we're going to look at this one a little bit sideways today. And we're going to try and do this actually in terms of y. So what we want to do is we're going to look at all of the y values on this interval. Right, we know this is the point 4, 2. So we're going to look at all the y values between 0 and 2 and say for all the y values, is one of the functions always to the right of the other one? So suppose I pick this y value. Which equation is to the right of the other one?
X minus 2.
X minus 2 is, right? Yeah, I would agree. Okay. What about here?
Still,
Still x minus 2. What about here?
Still x minus 2.
But all the way up there, right before I get to 2. Should still be x minus 2. Would you all agree?
Yes.
All right, so if one function is always to the right of the other for all y values in the region, you can integrate in terms of y. And we will do the rightmost function minus the leftmost function. And the reason we do the rightmost function minus the left, well, those are the ones that have larger x values. So we're finding the area, effectively, of this whole region, and then subtracting this region from it to just leave us with this one little piece in the inside. Does that make sense?
What are the benefits to doing it in terms of y rather than x?
Well, for one, I don't have to break this up into multiple different regions, right? Or I don't have to knock off sections of geometric shapes. And two, there are some cases in which I might have something that is so awful looking. For example, what if I gave you something like this function and this function and said to you, find the area of the region enclosed by those two equations? Well, I mean, there's a lot of issues with this. One being that at, let's say, even at x equals 0, the upper function and the lower function are the same function, or the same equation, right? And then there's more values over here at x equals 0, or even like at x equals 1, let's say, right? I mean, I have 1, 2, 3, 4 different times that my equation has an x value of 1. So that becomes a real issue. Whereas if I did it in terms of y, no matter what y value I choose, this linear piece is always to the right of this weird little squiggle that I've got. Does that make sense?
Yeah.
Yeah. So in this case, it's not of much benefit, but we're just doing a nice easy one to see how it works. And so what we'll have to do is we'll have to turn these into terms of y. So instead of having y equals x minus 2, we need to have x equals y plus 2. And instead of having y equals root x, we need to have x equals y squared. Good or no? So we have to turn it into terms of y. So what's our lowest y value of this region?
0.
And what's the highest y value of this region?
2.
2. So we'll integrate from 0 to 2, the rightmost function, which was x equals y plus 2. minus the the leftmost region, which is y squared dy. Good or no?
Good.
Great. And so this becomes y squared over 2 plus 2y minus y cubed over 3 from 0 to 2, which is 2 plus 4 minus 8/3 minus a whole big 0 over there for the rest of it. And 6 is 18/3 minus 8/3 is same thing we got all 3 times last time. 10/3 units squared. Good or no? So we can see that there are a lot of different ways that we can go about solving this same problem. And none of them are inherently better than the other one, just whatever makes sense to you is the best way for you to do it. But you do need to be able to integrate in terms of y, because we're going to have to do it for some area problems. And when we get into volume, there are some cases where it's got to be done in terms of y also. Any questions on that before we move on to the next thing? Next problem? All right. So I would like you guys to take a second and graph these two things and see if you can come up with a way to set up this integral to do it in terms of y. So I'll give you like 2 minutes to play around with it and see if you can figure it out. Ready, go. All right, so y equals x cubed looks something like that, and x equals y squared minus 2 is just a parabola. In fact, I'm going to draw that parabola a little bit better. There we go. That's not. There we go. We'll call that good. So pretending that this cubic that I drew actually went through the origin like it was supposed to, we're looking for this region. And the problem that sort of presents itself here is that for some of these x values, the upper and the lower part of the region are bounded by this parabola. Now, there are ways to get around that for this particular problem, but we're going to focus on being able to do this in terms of y. So is there one function that is always to the right of the other function for every y value from here to here?
Yes.
Which one?
The x cubed.
Right, which we should probably rewrite as x equals y to the 1/3. So we want an integral of that, y to the 1/3, the rightmost one, minus the leftmost one. And it's that simple other than finding these limits of integration. And so how will we find our limits of integration?
Find the intercepts, so set them equal.
All right, so, and we can't exactly set them equal to each other here unless we, replace the x with the y to the 1/3. So we can, from how we originally had it, we can't, but we could set it up now as y to the 1/3 equals y squared minus 2. And we want to do it in terms of y because we want the y values. And so either on your graphing calculator, well, actually, how about on your graphing calculator for sure, just solve that. I was going to say I could do it on Desmos also, but why don't you guys tell me what it actually comes out to be on your graphing calculator? I know the lower one is -1, but that one's pretty easy to just see. But the upper one is a little bit more difficult. So figure out what that is and let me know. Just 1 point something. What did that come out to be? $1.793037. Cool. Great. All right. So since we have a really heinous number to evaluate this at, we'll just use our calculator to approximate that integral. And let me know what you get. $4.215. That sound right to other people? Anybody else get that?
Yeah.
All right, perfect. Cool. Any questions or issues with that? Okay. So just to sort of recap everything we've been doing, our area underneath the curve just means the area between the x-axis and the curve. If we've got a region above, that comes out to be positive. If we got a region below, it comes out to be negative with the integral, so we have to take the opposite of it, right? We can, if we have our two different functions that we're looking for the area between, we can just subtract them, the upper minus the lower, without regard for where they are, above or below the x-axis. Everybody good with that? And if we are looking for the area of a region that is bounded by multiple different things on either the top or the bottom, we can maybe look for pieces to break off, like geometric pieces, or we can split it up into multiple integrals, or we can try and do it in terms of y, like we did with these. Everybody feeling pretty good about the area stuff? I don't want to do this one. We're going to do this one though. This will be the last one that we do.
Yay.
Oh, and something happened. All right, so we have cosine x and we have sine x, and we're looking between 0 and pi over 2. Pi over 2 is where sine hits its max and cosine hits the x-axis. So we're looking at two different regions. Okay. And so in order to find the red one, we're going to have to do an integral of cosine minus sine. And then we'll have to add to that an integral of sine minus cosine. Everybody agree with that? Cosine is above sine for this first part, and then sine is above cosine for the second part. And we know that sine x equals cosine x, that x equals pi over 4. So this should be from 0 to pi over 4. And this one should be from pi over 4 to pi over 2. Good or no?
Good.
And so our integral of cosine should be sine x. Our integral of negative sine should be positive cosine x. And then our integral of sine should be negative cosine x, and our integral of negative cosine should be negative sine x. And pi over 4 to pi over 2. And from there, we'll just evaluate. The sine of pi over 4 is root 2 over 2, plus another cosine pi over 4, which is root 2 over 2, minus 0 plus 1 for the sine and cosine of 0. And then we'll add to this negative cosine pi over 2, and cosine of pi over 2 is just 0, so we'll put a 0. Negative sine pi over 2 should be negative 1. And then we'll subtract another negative root 2 over 2 minus root 2 over 2. So we got root 2 over 2 and root 2 over 2, which is root 2, and a negative negative root 2 over 2, and another negative negative root 2 over 2. So that's another root 2. So 2 root 2, and then a minus 1, and another minus 1 would be minus 2 units squared. Is that what you all got when you did it? Hopefully.
Yeah.
Hopefully that makes sense. Any questions on that?